In this chapter, we have discussed already what is the cell coverage and also the signal and traffic coverage. Yes. But how the signal reflects in flat and hilly areas, right? That means cell coverage is nothing but how much the area which covers the signals provided by the channels, right? You have to cover the 100% area to provide the effective communication. Generally, we are considered as a cell as an sectorship, right? But in practical, there are many irregularities in the areas, and also some of them have hills, and some of them have rivers. That means there are many uneven structures in the areas, right? Out of them, some of them are human-made, and some of them are natural. Like hills and rivers, all these are comes under natural terrains, and at the same time, the human-made structures like urban areas, semi-urban areas, open areas, these are comes under human-made structures, right? Just how the signal affects in both these areas. We have to calculate accordingly. For that, we have to use some predictive models, right? One of them is the predictive model is the Lee model. We already discussed in the last class. For that, some parameters should be calculated, right? Like ground incident angle or ground reflection angle to predict the coverage area of the particular cell. Accordingly, Lee model, there are three main parts. One is general condition, or a standard condition. Is the point-to-point predictive model or a Lee model, right? And the second one is obtain area to area predictive curves. Area to area predictive curves also obtain. And the last one is point-to-point model. Point-to-point predictive model is obtained by using the area to area predictive model, right? There are three steps in point-to-point model. By using this, we will predict the point-to-point model and also the path losses in different areas like hills or rivers by using the predictive models. Right? And also the path loss curves are also obtained by using these models. Now, in today's class, we will discuss about propagation over water or flat open area. Propagation over water or flat open area. That means the propagation of signals over water. Propagation of signals over water or the open area, which is flat. That means not an hilly terrain. So, on a flat open area. For that, we have to derive an equation for propagation over water or flat open area. The propagation over water is of big concern because the interference of the chances of interference are very high. The chances of interference is very high if you do not make an necessary arrangement. If you do not make a necessary arrangement, the chance of interference is very high. The interferences can be controlled if we know the cause of the interference only. If we know the cause of interference, then only we can control the interference. Right? The permittivities of like the river water, the fresh water and sea water are the same. The permittivities of sea water and fresh water are the same. Permittivity is defined by epsilon naught. Right? But whereas coming to conductivities, the conductivities of both these water are different. The conductivities of both these waters are different, whereas the permittivities are same. Why we need this information means the signals are propagated over water or through water. For this purpose, we have to calculate the parameters in different waters. If the two antennas if you consider the two antennas, one at the cell site is nothing but the base station, and the other antenna at the mobile unit. That means at the antenna built inside the mobile. If you consider these two antennas, and both these antennas are above the sea level. Both these antennas are considered to be above the sea level. There should be two reflection points are generated. There should be two reflection points are generated. The one is the first one is close to the mobile unit, and second one is this one. That means here there are two antennas, one is this and one is at the mobile unit. These both are above the sea level. Here is the water level is here. That means both the antennas are above the water level. For this, two reflected waves are generated. This one is first wave, this one is the second wave. The first one is nearer to the mobile unit. The first reflected wave is nearer to the mobile unit. The other reflected wave is away from the mobile unit, right? We consider the reflected wave is the land mobile propagation is very close to the mobile unit. Is very close to the is very close to the mobile unit, right? We have to find the field strength using these conditions. Of a fixed point to point transmission and a land mobile transmission over the water, right? By using these conditions, we have to find the field strength by using this general formula. Now, between two fixed stations are point to point transmission. Here, the received power P suffix R can be expressed as P suffix R is equal to P1 into 1 by 4 pi d by lambda whole square of 1 plus A suffix V. This is some exponential term, right? Here, PT is the transmitted power. We will calculate the received power by using this formula between two fixed stations. Where PT is the transmitted power, lambda is the wavelength of the signal, and D is nothing but the distance between two stations. D is nothing but the distance between two stations. Whereas A suffix V comma pi suffix V is are nothing but amplitude and phase. And the delta pi is the phase difference. Delta phase is the phase difference caused by the path difference delta D between the direct wave and the reflected wave. Right? Here is the formula delta pi is equal to beta into delta D. Whereas delta pi is the phase difference and the delta D is the path difference. Here the formula P suffix R is equal to Pt into 1 by 4 pi d by lambda whole square is the free space loss formula, right? Here are two situations. This one is a direct wave, another one is a reflected wave. Both these are over the water. Like H1 is nothing but height from the water level to the base station, and H2 nothing but the height from the water level to the mobile station. Right? To substitute complex terms, if you substitute the complex terms, then the equation becomes like this, where P suffix R is equal to P naught of 2 minus 2 cos delta pi, whereas delta pi is the function of a delta D. Whereas h1 dash is equal to small h1 plus capital H1, which is the height of a antenna at the base station, height of the antenna at the base station. Another one is above the sea level, which is antenna height 2. H2 dash is equal to small h2 plus capital H2. H2 dash is equal to small h2 plus capital H2. Whereas h1 h2 are actual heights, and capital H1 and h2 are heights of the hills. Both antennas at fixed stations are high. Then the path difference can be calculated as delta D is equal to this formula, h1 dash plus h2 dash whole square plus d square. Other one is h1 dash minus h2 dash. Finally, the equation becomes two h1 dash h2 dash by d delta pi is equal to 4 pi h1 dash h2 dash by delta t. Yes, sorry, lambda t. Now, by substituting these conditions, P r less than P naught. P naught is nothing but the received power at the free space. P r is the received power. First one is P r less than P naught, then 2 minus 2 cos delta pi less than 1, or delta pi is less than pi by 3. That means delta pi is less than pi by 3. Right? If we substitute Pr is equal to 0, that means received power is equal to 0. This is the second condition. then delta pi becomes pi by 2, which is of 90 degrees. Another one is PR is equal to P0. That means the received power is equal to the power received at the free space. The power received at the free space is equal to plus or minus pi by 3. Delta pi is nothing but the phase difference is pi by 3. Or if PR greater than P naught, if PR greater than P naught, then the phase difference is between pi by 3 to 5 pi by 3. The phase difference is in between 5 by 3 to 4 pi, 5 pi by 3, right? This is the fourth condition. Now, the received power P suffix R is equal to 4 P naught. Then the delta pi is equal to, or the phase difference is equal to pi. Here is the values of delta pi for different for 5 conditions. You can found the phase difference from delta pi is equal to 4 pi h1 dash h2 dash delta 2 by lambda t, right? We can calculate the delta pi from this equation by using some examples. Right? Now the delta pi is equal to 4 pi h1 dash h2 dash by lambda t is for between two fixed stations, two fixed stations. There are two conditions. One is between two fixed stations, and the other one is land to mobile transmission. Land to mobile transmission. In propagation over water, there are two conditions. One is between two fixed stations. Other one is land to mobile transmission over water. This is the second one. Here, the land to mobile transmission over water there are two equal strength reflected waves. One reflected wave is from water, and the other is from the proximity of the mobile unit. One is the direct wave. One is direct wave. Out of these, the reflected wave, the whose reflected point is on the water, is considered because no surrounding point near this point, near the point. The reflected energy is strong. From now, the total received power is nothing but the summation of these three waves. On the direct wave, and the first reflected wave, and the second reflected wave. Because of minimum attenuation. Because of minimum attenuation. The above is the formula. P suffix r is equal to PTB for d by lambda square. Now here the delta pi 1 and delta pi 2. Whereas in both fixed stations only delta pi is considered as the phase difference. Now here the pi 1 and delta pi 1 and delta pi 2 are the path length difference. Path length difference between direct wave and two reflected waves. That means from direct wave to first reflected wave is nothing but the delta pi 1, and from the direct wave to second reflected wave nothing but the delta pi 2. They're generally very small. By adding the complex terms in terms of cos and sine, the equation becomes like this: 1 minus cos delta pi 1 minus delta pi 2 sine delta pi 1 plus delta pi 2. Right? So here the sine theta is equal to theta. Into the approximation, where the cos theta is equal to 1. Follow this approximation. As equation reduces to P suffix r is equal to, that means received power is equal to transmitted power by 4 pi d by lambda whole square. Right? This is the equation for received power. This is the equation for received power or power land to mobile transmission. This equation is also same as the received power from free space. Right? The path loss from the land to mobile propagation over land is different from the land to mobile propagation over water. Right? This is about propagation over water or flat open area. This will be calculated in two ways. One is between the two fixed stations, other one is From the LAN to mobile station. Then LAN to mobile station. Connect voltage loss. This one is effect of the human structures. It was discussed in the last class. Effect of the human structures. These are high spots and low spots are there. Accordingly, we will improve the quality of the communication based on this predictive models. This is about the Lee model. Lee model, there are three main steps. Out to the standard condition, area to area prediction model, point to point prediction model. Obtain of point to point prediction model by using area to area prediction. Right? General introduction. Right? This was the syllabus, cell coverage for signal traffic. In our syllabus, which is the a second part of the third chapter, cell coverage for signal traffic. Effective human structure, phase difference between directed and affected paths. That's the formula for mobile propagation over water and flat open area. And in coming chapters, we will discuss the path loss from point to point prediction model. Path loss from point to point prediction model in different conditions. Okay. We will discuss the next topics in next class. Thank you all of you.